I was reminded by Ileana's finished partial statement that I think is always useful for all scientists and engineers to keep in mind, especially when speaking to the public. So a statement attributed to George Box: all models are wrong, but some are useful. Remember that. I'm going to tell you about a project from which I've been the leader, but I'm speaking for a large number of people and a large amount of money that started 3 years ago. We're partway done. It's funded partly by HHMI at Genelia and the Allen and the Wellcome Trust and the Gatsby, who gave their money to the UCL, partly to help them do this and partly because in their infinite wisdom the EU wanted to charge VAT on money sent to a research project. They're designed and fabricated at a place called IMEC in Leuven, Belgium. This is a property of the Flemish government and also a nonprofit. A genuinely world-class fabrication capability. And testing is done at the 3 sites below. So, the design criteria from my perspective is, so first of all, Yuri talked about, well, we need a generic probe because they're too hard to make every one for everything. And so this is my notion of a generic probe, but I'm going to quote one of my colleagues, Karol Swoboda, who said, remember, never try and do anything that's better than 80% of the problems for 80% of the people. If you try and fill the corners, you'll fail. And so this is an 80-80 probe. So we're testing the very first complete designs of the ambition of the project. The project is supposed to complete in about 18 months. They're going to be available to all comers, we hope, by early 2018, not long after we complete. IMEC wants time to learn how to make them fast enough to supply the demand. I assume we will license them to be sold through other entities, but IMEC is obligated to sell them to you if you walk up to their window. And so this was something that Ken, whose now weary shoulders we're all standing on, this is the critical issue. We don't need another paper about probes. We need probes. And so you have to go someplace that's whose job it is to make things and not to teach students, because that's not what they do. So my parameters, what did I want to have for sure? Well, I didn't want an acute probe, and so chronic stability, and I work at a place where the most complicated and socially difficult animal is a rat. And so my notion, I asked what's chronic, and Albert Lee said 8 weeks. I said, okay. And this, in my opinion, is just driven by Schenck dimensions, as both Kenneth and Yuri said. If it's skinny enough, you seem to, from the standpoint of a physical scientist, late to neuroscience, if we want to understand the brain, first poke a hole doesn't sound like a great strategy, but it seems to be okay if the hole's small enough. And so poke a small hole if you got to poke a hole. And then site density has to do with how redundant your information needs to be, and this is mostly folklore. There's not really good quantitative information that tells you just how many sites, how close together, measure what part of the brain. And so the typical has been sort of 12 to 25 spacing in the most dense, giving us spike sorting leverage. Typical site sizes are 10 to 300 square microns. There are probably applications and maybe advantages for really little sites, but then you run into technology problems. So we're going to live up here. And then Schenck width, historically has driven site count. Our lithography is pretty lame. We can't put very many sites. Well, we can put as many sites as we want on a Schenck. The problem is we can't get the signals out. And so, again, speaking from history, 50 seemed to be okay. Could live with that as long as it was thin. Again, we're swimming in the wake of Ken here. 70s seems to be safe, but we're getting dangerous. And in my experience, specifically with people sticking things in, you lose chronic stability somewhere around 100. And so that means we got to stay down here. So the problem is that my engineering contractors and everybody else seems to be sort of stuck at this 1 to 3 micron line pitch lithography, and 1 is actually pretty hard. And that means you can get maybe 48 or 64 sites, but I'm going to show you where the world really lives here in a second. And you need more than 100. You'd like 1,000. So My problem is that I talked to IMEC and they said, okay, we'll do this, which is actually the biggest step in the whole program. You need someone who can do it that will do it. There are 30, 40, 50 places in the world that can do this. I'm not sure there's anyone else that will do it. And so IMEC says, well, we're going to make switched and active probes, and we'll give you 180 channels on a 50 micron wide shank or 384 channels on a 70 micron wide shank. Well, it may seem like a stupid thing to do to build a probe to answer that question, but 200 channels are at stake here, and so this is worth doing. So we made this probe. This probe was actually made by Brian Jameson's company, SB Micro. And Brian, I think we should call these Potomac probes, because like I'm on Virginia, Brian's in Maryland, and so they need a name. And so I proposed Potomac probes. And so anyway, we tested these for chronic stability in the hands of, get a slide out of place here, or I missed a slide. Well, I guess it's skipped. So let me just tell you the result. Both of these were comparably chronically stable. 8 weeks, no visible degradation of signal for either 50 or 70. Now, one of the problems in neuroscience is our statistics are weak. You can't do 1,000 rats with 2 probes each. That's what semiconductor guys do. We can't do that. And so as far as we can tell, within the bounds of biology experiments, you don't get into trouble here. And so, fine, we'll go with that. So, what did phase 1 do in neuropixels? Well, we needed a low impedance site, and gold is really dangerous in CMOS clean rooms, so that's probably not a good idea. They poison silicon circuits, and electrodeposited polymers, which are my favorite site at the moment, are just incompatible with semiconductor processing. And so IMEC proposed porous titanium nitride, which as far as we could tell at the time didn't exist. But they invented it for our project. A 12 by 12 micron site, 144 square microns, has an impedance of 130 k ohms when you start. James John, my postdoc, sticks it in a rat. He waits 8 weeks. We have no loss in activity. He pulls the probe out and sticks it directly into buffer without rinsing, and the impedance is still 130 k ohms. And so that material is golden. However, it's a secret. I cannot tell you anything else about it except for what I just told you. I know nothing more than it's porous titanium nitride, and it seems to have great chronic stability. So this is what chronic stability means in our hands. So this is a long-standing argument between Kenneth Harris and me is, what do you mean? And so Kenneth says, measure the 90th percentile spike amplitude. And so there are 4 shanks on the probe, and so you can see each of these 4 shanks. And the bottom line is not much is going on. And so that's the good news. So then Yuri's already told you about part 2. So part 2 is we need a probe with sites everywhere. And that requires lithography that is outside the bounds of university capability. So this is the first probe in the project. It is 7-layer metal, 130 nanometer aluminum on CMOS on SOI. That has probably never been done anywhere else because it's a very odd combination. IMEC was afraid that copper would diffuse through the silicon and poison neurons, and so they didn't want to use copper. So copper, you do 90 nanometer, we could have done that, and so they did do 130 nanometer because that's where aluminum lives. And apparently there had never been any simulations of 130 nanometer aluminum on CMOS because nobody does that, and so it's a kind of a unique technology. Again, it's one of these things is how lucky you are to find somebody who can do it that will do it. And so this is our initial idea of sites everywhere. It's 2 sites every 20 microns. They're 28 microns apart. The design rule that IMEC imposed on us was no more than 5 microns close to the edge. That seems like a long way to us who make conventional, simpler probes. And this goes on, you know, as far as you want. And so the length of this shank is 10 millimeters. The width is 50 microns. We tested thickness of both 20 and 35. We didn't test 35 in depth, but in fact, we didn't run into too much trouble with respect to chronic stability at 35. there are 128 analog channels out, so there's no multiplexing in this part here. It's just a bunch of wires going to the base. And so they wire bonded out 128 channels, analog input into conventional INTAN-based multiplexing sites. We actually built our own recording system at Genelia to do this 192 channel system. But I'm going to tell you briefly about these because this was the first test for active sites. So 2 of the versions of this had an amplifier under every site, unity gain, so it would be a low impedance path to the base. And the other 2 had switches so that I can select among all of the sites on the base. What did I show next? So this is what the geometry of that probe looks like. So we only have 128 lines, you know, sort of wire bonded out here in this mess of wire bonding. And so, but we wanted sites everywhere. And so this is a 900 site probe, and it's in 5 groups of 180 because this one has a skinny shank. And 128 of these are accessible by switches, so I can choose this one or this one or this one, or various combinations of them, not quite random. And then the third thing that we did that's unusual is we put reference sites on the shank, just in case you wanted them. So you can program these in. There are no base electronics. The 2 options had 128 wired out, 2 options had 128 of 180, and you can switch. So this is what it physically looks like. I'm not going to spend too much time on it, but I think Albert Lee this afternoon is going to show you a little data from one of these probes, and so I just wanted to point out physically what it was about. They're pretty awkward, but they work, and we did chronic stability, and they were fine. So now to part 3, which is where we are in a 4-part problem. So now we put everything on the probe. So this is a recording system built directly into silicon. All you got to do is get the data out. So all the amplification and the multiplexing takes place here. And then you have sites everywhere down the shank. And so we built 4 versions. 2 are 5 millimeters long because we thought, well, the mouse guys don't want these really long probes. And then all the mouse guys wanted really long probes. 1 is a strictly, I can do better lithography than you can probe. Just passive, you know, 384 lines out in a 50 micron wide shank. You know, I can do 16. Shows you the level of lithography advances. And then that with amplifiers under every one to see if you like it, but to fit the amplifiers on, you had to push it out to 70 microns. And then this, but sites everywhere, 960 sites, 384 out at a time. Selectable with switches under every one. Again, you're sharing 384 output lines, and so you know, if you turn 2 on that have the same output line, you might be confused, but on the other hand, there's recent information that you only have 2.5 sites per output line, and there are people arguing informatically that's manageable. And you could probably turn them all on and sort the data out in a spike sorting like environment, except for LFP would get very confused, so you'd have to leave a few left over. Yuri will give you that recipe. He knows more about LFP than I ever will. And then the last option, again, is one of these things that for active sites, we put an amplifier and a switch on every site, but now we used up too much shank width, and so we could only fit 276 channels out in a 70 micron wide probe. And so this doesn't make me happy because I gave up 100 sites, so only if I really need it. And then Yuri's reminder that we must make them light tolerant because optogenetics is the use of the day. And so this is what they really look like. These things do exist. So here's the probe, and it comes, so here's the probe right here. Well, let me start at the bottom. So now here's a picture. This is the real deal. So this is a 70 micron wide device, and we decided to zigzag the sites. It's 20 microns between every 2, and we decided to zigzag them because it looked tetrodish, and maybe we'd get geometric spike sorting advantages. And these things are made out of porous titanium nitride. Thank you. You can have the one with dead batteries. Then you have to get the signals out, and so I actually don't quite understand why you need so much space, but this thing is glued and wire bonded out to a piece of flex. There's 60 channels in the flex. You have to remember now that at the base of the probe, you have a 384 channel amplifier multiplexer network, and out comes a gigabit a second of data. So you do not transmit a gigabit a second on any old piece of flex, like the stuff that I make or the stuff that Yuri's been using. You just get all kinds of errors. And so you actually have to be really careful about how you do this in ground planes and all that jazz. Now you're talking, I mean, these are nanosecond pulses. And so then you get you get out here, and this is the head stage. It only weighs a gram. Uses a little more power than it should because of power supply design. That's a fixable problem. And all this does is tell the probe what to do, and there's a serial deserializer network, and so this launches the data down a 5-meter cable to the wall, because if Albert Lee is your collaborator, you need a 5-meter cable. Down here, where you cannot read, it says, C.M. Lopez et al., ISSC 2016. Exactly 45 years after Ken's ISSC initial publication. This is where you put your best stuff if you're an electrical engineer. And so there's a paper about this. It's actually an abstract, but you can read about the architecture of this device. And so, you know, the word is out electrically as to what we're doing. And then the system looks like this. So you saw this picture already. So here's the probe. The flex plugs into a ZIF connector in the base. You have this 2-coax cable for the moment, 5 meters of cable, going to this little printed circuit board. And so you can see that this is about 4 inches square. And that's one of these amazing FMC 250 pin connectors. It's an industry standard. And then that plugs into here. Actually, it plugs in right there. So this is a commercial FPGA evaluation kit board from Xilinx. It costs $1,600. And it's far more capable than what we're using now, but this was the fast way to get started. And we, in fact, don't plug this into a PCIe bus. We just take the data right out over Ethernet. And most computers, including the one I'm talking on, are more than fast enough to do Ethernet at gigabit, and so you're okay. If your laptop is truly ancient, you might need some help, but you probably need a solid-state hard drive because you're spooling data really fast. And then, you know, Nick Steinmetz wants to put TAN in. And so anyway, so that's it, is that it is now a 384 channel recording system that's gonna cost you less than $5,000, and most of it's reusable. So I brought one example of data because my postdoc works really hard and it would be unjust if I didn't. So here's a picture of one of James's rats with a probe on, and so it's much less awkward. This is one of these 15 milliliter plastic tubes that we all mix our reagents in. James likes these. He glues this on the head of his rat. The probe's buried inside there, inside of a lot of acrylic. This is the flex out. The head stage is glued to the cap of this with the hole cut out, and so he just spins it on and then plugs it in, and then hooks it up to the wall. And so this is a recording. I don't actually know how many seconds this recording is, but you can see each of these is a spike, and all 348 channels 384 channels are pouring out at once. I mean, there's 374 because 10 of them are references. And this is in the prefrontal cortex of a rat during sleep. And so when I went and asked my colleagues, what should I test? You know, I have 10 rats running at the same time. I want to record from them 3 times a week. I don't want to train them to do anything. I think it was Ava actually said, do sleep. They know how to sleep. There's interesting things going on. And so I'm going to leave the rest of the science to my colleagues. Nick Steinmetz has a fantastic poster tomorrow, and Kenneth has some data from the UCL group, and Albert's talking this afternoon. So this is the other piece of good news, having nothing to do with the probes themselves, is that I was afraid I was just getting ready to drown us all in data because our spike sorting software was so slow, we were just gonna pass out. And so that James wrote a new package that he calls Juniorclust, and there are at least 2 others that are comparably fast. And so this is the digestion of that whole recording of 10 minutes. It's around 1.4 million spikes in 10 minutes. He claims there are 528 clusters in here. So you can manually curate this in real time if you like and decide, are you believing there are 528 clusters in here? But this digestion took less than 20 minutes. This would have taken 2 weeks last year. So the status of the project. I told you I was going to tell you about this. So far, there are no clear advantages to active sites. Our best test is to tap that little head tube with a cable tie. You get some really nice vibrations, like the rat banged its head on the wall of its enclosure or on the maze. You see transients, but the transients are so uniform across all of the sites. If you simply subtract the median signal, you see no spike detected based on that amount of data. Whether or not you could find one spike right in the middle of that transient, I think remains to be seen, and we haven't done that experiment, but mostly that works the same for active and passive probes. So you don't have to worry about the fact that an active probe, a transistor amplifier, is an outstanding optical detector, about 50% quantum efficiency. And so if you shine light on it, you're going to see a big signal. We don't need them, apparently. We don't find a way to use them. That's good news for me in two reasons. One is I don't have to worry about optical sensitivity, and the second is that I don't have to give up 100 channels on that probe that had both switches and amplifiers, because now I don't need amplifiers. We see no measurable disadvantage from switches. It depends on who's making the measurements. Sometimes people say, I saw 0.3 microvolts of added noise on the probe with switches versus the probe without switches. But nobody who's done biology knows that matters. There's no power dissipation from switches. We worried about this because when you're running amplifiers, you're dissipating power in the animal's brain. Are you going to warm it up? There's no power dissipation. The switches are a memory buffer. So you just run a bit string into the switch and then you're done. And it just sits there passively all day. This question of multiple outputs per multiple sites per output channel, I think, is one that could advantage us all, because we could use cheaper technology to get more data. And the extra real estate, doesn't really, so 70 microns seems to be okay. So my answer to you is switches seem fine and amplifiers seem unnecessary. So what's next? So commercial release, as I said, early 2018 seems reasonable. The target cost is €1,000. I just looked it up in the Wall Street Journal today. That's $1,128. I have no idea what it'll be in early 2018. Maybe Brexit will tank the euro and it'll be cheaper, or maybe it won't and it'll be more expensive. But a bargain by any measure, and they're reusable. We would like a smaller footprint base. The footprint of this base is sort of 5 by 10 in round numbers. It's about 50 square millimeters. You could put 1 on a mouse if you're tolerant. 2 is not likely. And I wanted from day one a multi-shank probe. Tissue doesn't really align with a linear array of 4 millimeters. So I wanted to take my 100 channel or my 400 channels and put them on 4 shanks. Programmable 100 channels each, so that's about 1 millimeter. That's actually quite nice with respect to rodent geometry. I mean, you might need 4 millimeters if you do monkeys, but we don't do monkeys at Genelia. The problem is that I needed €1 million I didn't have in 2013 to make both multi-shank, and so we decided, well, look, let's prove we can do this at all. And then the things that Yuri talks about is do we want to put light bulbs on the probes or not? I would like this to be part of the panel this afternoon. The reason I was willing to go to the mat to sell this project is that I thought that you could make a nominally generic probe, the 8080 probe. Sites everywhere, programmable. I'm not as convinced that you can do that with photonics, as there's clearly photonic probes are really useful. But can you make an 8080 photonic probe? The answer is I don't know the answer to that question, and I want to hear other people's opinions. What would you be? I mean, IMEC would love to, me to give them another couple of €1 million and put light bulbs on these probes. They think they can do it, but the nature of those light bulbs is not generic in my understanding. And so this is where we would like to do. This is aspirational, meaning I need a really big check, but I think it's doable. It's actually a third of the size of the last check, so I'm getting cheaper. And so we want to. So IMEC says, look, we think we're smarter than we were when we started. We can actually make that base 3 by 6 or 2 by 9, 18 square millimeters. Keep all 384 channels, and make that in 4 shanks for you, and maybe fix it so that you can put all of your 384 channels on any shank that you want, or divide them up as you like. That's sort of an open question, but at the very least you could put 1 millimeter's worth of programmable shank sites everywhere on every shank. So this is when Albert said, so he asked me, what's the deal? And I said, well, it's in round numbers, 1,000 sites per shank times 4 shanks. And he said, you could put 4 in a rat. And I said, I think you put 10 in a rat, but 4 for sure. And he said, that's 15,000 sites and 1,500 channels in one animal. I thought, yes. And so I say again, Kenneth, you should be happy because it's taken a while.
Yeah.
But on the other hand, without all of that work to show what could be done, and then the great good fortune of IMEC being willing to do it, applying genuinely state-of-the-art technology to the problem in what is clearly a boutique space in microelectronics. And then I always go back to the very first slide, just the generosity of the nonprofits that wrote a check. So, the 4.2 million euros was checks sent to IMEC. That didn't count paying any of us. This is probably a $10 million probe. That would have been really tough to finance in a public grant. And because it's just one thing, we're not solving everybody's problems. And so I think the lesson here is that you can do it. You have to find, the right time and place. And without Kenneth, the right time would never have occurred. And the right place is, me landing there and Albert coming down and says, I want to put 100,000 sites in a rat. And Dima Renberg saying, I got this 4-site probe. Can't you do better? I thought, well, we should be able to. And so I think, Kenneth, be happy. I'm going to leave it there. Thank you very much.
I think you all know under Unswitched's leadership, U of M get awarded a NSF grant for international research and education. So that's the Partnership for International Research and Education.